This, I believe, will be our last lecture video. Um, we're going to talk a little bit more on differentiability. Now, obviously, the topic is endless. Unfortunately, this is probably what we can cover this semester. Um, Back there, we still have the chain rule, directional derivatives, and gradients, all kind of stuff. But this is where we're going to stop, okay? More on differentiability. Let's mention one connection between continuity and differentiability. Which is the same as a function of one variable, okay? Function of one variable. A function that is differentiable, a function that is differentiable must be continuous. Uh, Number two. A function that is continuous, and even with the existence of partial derivatives, the partial derivatives exists. A function that is continuous and partial derivatives exist. The function is not necessarily differentiable. So this is what we talked about in the last video. All right. A very simple example that you might feel you have seen it before. We look at this example here. This is where x and y is not the same. X and y is not the origin defined by this formula here. It is defined to be 0 at the origin. Show that this guy is not differentiable. If you look up the previous video where we have to calculate the partial derivatives, find out the linear approximation of the arrow, and then calculate the nonlinear part. Before you even do all that part, let's notice that this guy is actually not even continuous. That's something we can show real quick. Okay, so we'll simply say this guy is not differentiable because it's not even continuous. Since it's not even continuous. Well, actually at origin, okay? As far as why this one is not continuous, this is actually something that you have done before, where you have to calculate the limit at the origin. The limit as x or y approaches the origin, needs to be 0 for this guy to be continuous. But this limit does not even exist. As usual, we take a path, and we take a different path, like along the straight line here, and set x approaches 0. So when y is always mx, okay, when y is always a constant times by x, this ratio here turns out to be a constant that depends on m. All right, and this is enough to say this limit does not exist, and it cannot be what? Cannot be continuous. Yeah, so this is this guy. So what I'm trying to say here is actually this limit does not exist. Okay, this limit does not exist. I probably shouldn't write this way. I probably shouldn't write this way. I probably should just say because this is m over 1 plus m squared, that's why this limit what does not exist. Okay, that's what I mean. So that's a quick application of the fact that a function to be continuous, the function may not necessarily be differentiable. Sorry, it's definitely not. It's not necessarily differentiable. Next topic is the mean value theorem, which is similar to a single variable function, and we have a associated mean value theorem for function of two variables. Two partial derivatives in some neighborhood containing x naught, y naught. So not just at this point, okay, but exists around this guy. Then for any point in the neighborhood, there exists 2 points, okay? 2 points in R2. So A1 is actually a point in R2. In other words, it's a pair of numbers. A2 is also a pair of numbers, such that the difference between those two functions values here, so this is the function's value at x naught, y naught. This is a little bit away from x naught, y naught. Mean value theorem. It claimed this guy equal to partial derivative of f with respect to x. So this is a partial derivative. Evaluated at one point, a1. So once again, a1 is actually a pair of number. For example, 1, 3. Meaning you're going to plug in x equal 1, y equal 3. Times by x minus x naught. Times by y minus y naught. That's the mean value theorem for a function of two variables. You can easily compare this with function of a single variable. Mean value theorem, here's how mean value theorem single variable look like. Right, f of x, a, b. Mean value theorem says f of b minus f of a equal to f of b minus f of a equal to the derivative at some point, let's call c, times by b minus a. See how this can be compared to each other? So you do partial derivative times by b minus a. The c is located by sketch a tangent line here. Remember that? So that's the c. By sketch a parallel tangent line. All right. So that's the mean value theorem for single variable function. That's the mean value theorem for function of two variables. So the key here is I need a partial derivative to exist in the neighborhood. All right. And then we say there are two different points. In function of a single variable here is 1 point, that's C. Here we need two different points where the difference between the function's value can be approximated by two linear arrow. Did you notice these are two linear arrow? That's a linear arrow, that's a linear arrow, followed by some constant in front. All right? And that's the mean value theorem, okay? That's the mean value theorem. And because of this mean value theorem, we can come up with the following important conclusion on differentiability. So this is a very important result. The result claims that if the partial derivative exists at x0, y0, then f will be differentiable at that point. Well, you probably all realize that this is not true. We just said partial derivative exists. It's not enough to say this guy is differentiable. However, if you add an additional requirement, if this guy not only exists, but actually continuous. So partial derivatives are, some continuous function. That turns out to be enough to say this guy is what? Differentiable. Think about that, all right? So if you can calculate partial derivatives and they exist at that point, and they both turns out to be continuous functions, that'll imply this guy is what? Differentiable. The proof, I like to prove this and then provide one example, and then that'll be the end of this lecture here, okay? So let me show you why this is true, why the continuity of partial derivatives, imply the function to be differentiable. Turns out this is a direct application of mean value theorem. For any x and y in this neighborhood, so for any x, y, so that's a point. So there is obviously this arrow or difference between the x value and y value. So we can let x to be a little bit different from x naught. So that's the perturbation here. And y to be y naught plus delta y. Because our goal here is to prove this guy is what? Differentiable. So you look up the definition, which requires us to calculate this difference here. So that's the function's value at x and y minus the function's value at x naught, y naught. I want to calculate this and show you the nonlinear part goes to 0. Mean value theorem, okay? Mean value theorem says this can be approximated by, or actually not approximate, but equal to partial derivative at some point a1 times by delta x. a2 times by what? Delta y. That's the mean value theorem right here. That's the mean value theorem right here. But if you look at the arrow part, there's this linear part and nonlinear part. The linear part, it is partial derivative evaluated at x naught, y naught. Not at a1, okay, but x naught, y naught. So I like to rewrite this into the following format. But they are obviously not the same, okay? They're obviously not the same. So I will make them equal. I will make them equal by rewrite this into this. At a1, so that's the partial derivative at a1, minus this guy. Times by what? Delta x. You see, when you add those two guys up, partial derivative at x naught, y naught will be cancelled, and that's indeed just this guy here. So I don't care the actual formula here, but these are the terms that's after the linear part, the linear error. Sorry, delta y. And if you look at this expression, so this is the 1, 2, 3, 4 different terms here. If you look at this and compare this with the definition of differentiability, I want you to look up the notes or that video and that part. You will see this component here, this component right here, that'll be that epsilon 1. All right. Like I said, epsilon 1 in this definition here is not a constant, okay? It's an expression. And that's your epsilon 2. Epsilon 2. And for this guy to be differentiable, epsilon 1 needs to go to 0, okay? Epsilon 2 also needs to go to 0. And that's something we need to show. Is that going to 0? Well, that's actually where the continuity comes into play. So here's the argument, okay? Do those two guys goes to 0? If they goes to 0, definition says, well, it's going to be differentiable. So since the partial derivative are continuous, so the limit of this as delta x goes to 0 and delta y goes to 0. So the limit of this expression that I wrote here, it'll be 0. It'll be 0. For those who are wondering why this implies this goes to 0, because when x naught, y naught goes to 0, this point, okay, keep in mind this point. So here's x, here's y, here's x naught, here's y naught. So we have a neighborhood surrounding x naught, y naught. A1 is a point inside this neighborhood. Okay, A1 is a point inside this neighborhood. As you are shrinking delta x and delta y, so this will be something like delta x. Down here is like delta y. The size will be delta y. As you shrink delta x, delta y, you will push A1. Okay, you push A1. Okay, you push this point. Approaches what? X naught, y naught. And the fact the partial derivative is continuous implies that those two limit has to be equal. Okay, has to be equal. This is equal to this. This probably takes some detailed explanation, but that's what it means. Okay, when delta x, delta y goes to 0, A1, okay, this point approaches x naught, y naught. It's being squeezed towards x naught, y naught. And that's why. And that's exact that epsilon 1 that I denoted. The same story. The limit of epsilon 2, which is that expression up there, also goes to 0. By definition, f is what? Differentiable. A quick remark is this. The partial derivatives being continuous, the continuity of partial derivatives, it is a sufficient condition for differentiability. That was the theorem says. Okay, as long as this partial derivative is continuous, that implies the function to be what? Differentiable. But It is not necessary, okay? It is not necessary. So there are cases, even when the partial derivatives is not continuous, the function may still be differentiable, okay? May still be differentiable, but it's not necessary. To illustrate what we're saying here, I will show you a tricky example. Let's look at this two variable function here. Away from 0 and at the origin. Let's look at this guy here. I will show you that this guy is differentiable, but the partial derivative is not continuous. Show the partial derivatives is not continuous at 0, 0, okay? Because everywhere else, you probably notice it's probably going to be continuous. At 0, 0, it's not continuous. But f is actually differentiable. So that's the key today, okay? Partial derivative, continuity of partial derivatives implies differentiability, but it's not necessary condition, okay? It's not necessary condition. So let's look at this example here and think about why the partial derivatives is not continuous. To talk about continuity of the partial derivative at 0, 0, I have to calculate the partial derivative at 0, 0 and the partial derivative away from 0, 0, okay? So solution, let's do the partial derivative at 0, 0. This is done by definition. We perturb x a little bit. Y is always kept at 0. So obviously when x and y is 0, 0, it's just minus 0. And back here, we have, I can use delta x here instead of h, okay? So it's delta x squared and sine 1 over delta x squared. Divide by, well, delta x. We're going to let delta x goes to what? 0. That's the definition of partial derivative. Previously, we have used h here, but here I use delta x, same thing. The fact that sine x is between -1 and delta x goes to 0 implies the limit of this is 0, because you have delta x squared on the top. Same story. By symmetry, partial derivative 0, 0 with respect to y is also 0. When x and y is not at the origin, to calculate the partial derivative with respect to x, I will simply use this formula here and apply the product rule. All right. So doing the partial derivative with respect to x, differentiate x squared, I get a 2x, and I leave this guy alone. Followed by leave this term alone, differentiate this by a quick chain rule, okay? So minus, so I want you guys to verify this by yourself. This part is the derivative of sine 1 over x squared plus y squared. Verify this by yourself. So that's the partial derivative away from the origin. Why is this guy not? Why partial derivative is not continuous? Since let's look at this limit of partial derivative as x and y approach 0, 0. The fact is, okay, this limit actually does not exist. And I leave this to you, okay? Turns out as x and y approach 0, 0, this limit does not exist. For this guy to be, for the partial derivative to be continuous, I need the limit equal to what? Equal to 0, okay, equal to 0. But the truth is, this term that you're looking at here, the limit does not exist, okay? The limit does not exist. Now, once again, for those who are wondering why this does not exist, you think about this, okay? Think about this. This guy always goes to 0 for sure because sine is less than 1. 2x goes to, this guy goes to 0. The problem is this part, okay? The problem is this part. Anyhow, the conclusion is those two partial derivatives are not continuous. However, this does not prevent the function to be differentiable. This does not prevent the function to be differentiable. Let's think about how do we prove differentiability. Remember this: f of x naught plus delta x. Sorry, that's not right. F of x naught plus delta x, y naught plus delta y. We're supposed to calculate this and subtract what? F of x naught, y naught. That's like the change in the function's value. That's not delta y, rather delta f. That's like delta f. X naught, y naught, 0 here. X naught, y naught is 0 here. So it turns out this is just what? Delta x squared plus delta y squared. This guy back here is just 0, okay? So that's what it is. So I want to somehow do the partial derivatives. The partial derivatives are all zeros. Use the partial derivative is 0 times by delta x, partial derivative times the delta y. So this is the linear error. Linear error. Plus some higher order terms. We want to prove that part goes to 0, okay? Goes to 0. Plus epsilon 1 delta x and the epsilon 2 delta y. So I want to compare this guy with this part here and try to figure out, I want to compare this guy with this part here and try to figure out what's my epsilon 1, epsilon 2 and show they, both goes to 0. So if you quickly compare them, okay, here you have delta x squared sine, and that'll be our first part, and followed by delta y squared times by sine, that'll be my second part. So I can rewrite this as this, okay? It's delta x times by sine times by delta x. So that's delta x squared. So that's like the first component, and that's my epsilon 1. So I'm rewriting this expression into this format, okay? Format. I know it's kind of tricky, but that's the way to go, okay? That's the way to go. And this is my what? Epsilon 2. The definition says if those two parts, goes to 0, okay? If those two parts goes to 0, when delta x, delta y goes to 0, then it'll be what? Differentiable, okay? It'll be differentiable. So do you think those two parts goes to 0? When delta x, delta y goes to 0, kind of trivial. Once again, because sine is a finite number between negative and 1, and delta x goes to 0. So I would say this is trivial. And then it's become trivial that epsilon 1 and epsilon 2 both goes to 0. As delta x, delta y goes to what? 0. So think about that. And that's how we come up with the conclusion that f will be what? Differentiable. All right. So what we learned in this section essentially is the fact that continuity of partial derivatives implies differentiability, but it's not necessary condition. Okay, it's not a necessary condition. And like I said before, there are plenty of other topics. We have the chain rule, we have mixed derivatives, we have gradients, we have maximum minimum in terms of function of two variables. These are all potential topics, but unfortunately, that's where we have to stop.